Welcome to the Ultralight Airplane Workshop. My name is Leon. Let's find out what the final, or possibly final, wing configuration is going to be for the UWS-1 Ultralight Airplane. Well, I'm pretty excited about this step. I now have the overall configuration for the UWS-1Design figured out, at least for the main wing. Let's get right into it. Well, to start with, I've decided to go with partial span ailerons and partial span flaps. I had toyed around with full span flaps for quite a while, doing some calculations, looking at different kinds of flaps and the ailerons I'd have to use to go with full span flaps. I finally decided it was going to be a little too complicated and a little bit too heavy. That doesn't mean I won't try it in the future, but I decided for the first iteration of this airplane, let's make it just a little bit simple, and we'll just go with the slotted ailerons and double slotted flaps. Now that means the flaps are a little more complicated than you'd have with single slotted flaps or plain flaps. But I think that the little bit of added complexity and a little bit of added weight will probably pay for itself in a smaller wing. I will probably also play with changing this hinge point of the slotted aileron, maybe move it up just a little bit. I'll have to toy with that just a little bit. I haven't completely decided on the chord of the aileron. I'm thinking right now probably around 25% of the chord of the wing, but I will have to look into that a little more. I will also probably not have the slot open when we're in the neutral position. We're in the cruise mode. I'll probably try to have that slot closed. But that's some details I can work on a little bit later. So at the moment, I'm thinking that the ailerons will be around 30% of the wingspan, and the flaps will take up 70%. But along with that 70% is going to be the fuselage and the engine nacelles. So in reality, the flaps will be just a little bit under 70%. Now on these flaps, I'm probably going to stick with the configuration that we're seeing here, where the nose to tail chord of the flap is around 30% of the chord of the wing. That's not shown here, that's shown in another picture, but I kind of wanted to demonstrate what the deployed aspect of the flap is. I will probably not use this pivot point to get those extra degrees of deflection. I will probably stop at 45 degrees. You can go up to 65 degrees deflected if you pivot around this point also. I'll probably only pivot around this point, so that'll give me 0 to 45 degrees of deflection. That's plenty. And it makes it a little bit simpler. So now we need to figure out what is going to be the coefficient of lift max of the wing, given that we've got these double slotted flaps and they're roughly 70% of the span of the wing. Here is a top view of the wing in green. You can kind of ignore the rest of this that's in gray. Right now these are just rough guesses of what I'll have for the fuselage and the nacelles, position of the motors, and the tail section. For example, this will probably be pretty smooth over the top here. The fuselage will not stick up past the top of the wing, and the nacelles will not stick up past the top of the wing. So you can ignore that. But the configuration of the wing, I believe, is what I'm going to end up with. Now, I've talked about in a previous video how I came up with the planform for the wing. This is basically elliptical until it gets out the tip. So it's a cut-off tip elliptical form. I put more of the curve of the ellipse in the front and less in the rear on the trailing edge to make it a little bit easier to make my flaps and aileron. I didn't want a large curve back here, so I'll put most of the curve up front. So out here on the tips will be my ailerons. Inboard are flaps, and outboard of the nacelle are flaps. So these will come down together and be double slotted flap. The hinge point for the flaps will be on the fuselage, on each side of the nacelle, and I haven't decided if I'll have a little protrusion below the wing as a hinge or if I'll put a slot for the aileron to follow here in the wing. Probably a slot, but I'm going to have to postpone that decision a little bit later. If you are new to the channel and to the design series on the UWS-1 Ultralight Airplane, a factor that will be affecting this wing design is that the props are going to be driven by electric motors, and we'll use batteries to provide power to those electric motors. One of the things that may modify my ailerons out here are where I'm going to put the batteries. This wing, combined with the engines and batteries, is going to have a little bit more moment than your typical ultralight wing. Typical ultralight wings will have nothing out here except wing and ailerons. I'm going to have a motor. Now the motor isn't that heavy. I'm also going to have, I think, some gear out here. I think it'll be mounted to the wing, although I haven't decided on that definitively. But I also want to have the batteries fairly close to the motor, so I don't have wire losses with the huge amount of current that's going to go through the wires between the battery and the motor. I like to have that battery fairly close to the motor. That'll either be in the nacelle below the wing or in the wing fairly close to the nacelle. I haven't decided on that definitively, probably in the nacelle. But that puts a significant amount of weight out here about 3.5 feet from the center line of the fuselage. Well, that means I've got a fair amount of moment out here that when I want to roll, those ailerons are going to have to get that weight out there moving and rotating about the center line of the fuselage. That may make me wish I had increased the span of my ailerons. The nice thing about using these slotted ailerons is that they're a little more effective than plain ailerons. So that may help me out. Of course, one of the drawbacks to those slotted ailerons is that cruise, they'll have a little bit more drag than plain ailerons will. So the span is currently 27 feet. That's about 13.5 feet for the semi-span. And that gives me a root chord of about 3.9 feet. Tip chord is half of that, so that's 1.95 feet. In order to tell you how I came up with the wingspan and the root chord length, we're going to have to go through a few calculations. So if you're interested in those calculations, stick around for the next few slides. The first part of our calculation is going to be pretty easy. First, we need to know what the maximum lift coefficient for our airfoil section is going to be. Now, from a previous video, the UWS-1Design Wing Airfoil Selection Part 3, I designed a little airfoil that's based on the GA30U-615 Ultralight Airfoil from Harry Riblett. And what I did is I modified it to be a 15% thick airfoil with the maximum thickness at 35% of the chord, and to have a maximum camber of 3.5% at 42% of the chord. Next, I want to come up with the maximum coefficient of the wing will be, not the airfoil section. And we'll just kind of cheat and use Barnaby Wainfan's assumption that most good wings will have around an 85% lift efficiency. So if we take our 1.5 maximum coefficient of lift for the section, multiply it by our 0.85 lift efficiency, we get 1.275 maximum coefficient lift for the wing. And that 1.275 maximum wing lift coefficient is without flaps. Let's find out what the maximum coefficient of lift of the wing is going to be with flaps, when our flaps have a span that's 70% of our wingspan. Well, here's how we'll start. Since we already know what the maximum lift coefficient of our airfoil is going to be with our double slotted flaps deflected 45 degrees, and that came from our previous video, UWS-1Design Wing Size Part 2, we have 3.0 maximum lift coefficient. So that's our airfoil section maximum lift coefficient. We need to find out what our wing maximum lift coefficient is going to be with that double slotted flap only covering 70% of our span. Well, the method we're going to use wants to know what the delta or the difference in maximum lift coefficient is between having the airfoil deflected and not deflected. So what then we'll do is we'll take our 3.0 for our section lift with the airfoil deflected minus the 1.5 that we showed earlier when it's not deflected, and we get a difference of 1.5. So we're going to use this number for our delta CL max. So from Barnaby Wainfan's Airfoil Selection Part 7, we have this funny little equation here that says the change in the wing's maximum coefficient of lift is going to be the flap deflected change in airfoil section coefficient of lift multiplied by the span of flaps divided by the span of the wing. Now there's also another factor in here of 1.3, and that's if your flaps are 50% of the span or less. Well, ours are 70% of the span. So what we should probably do is an interpolation going from 1.3 correction factor down to 1.0 correction factor if the flap span went all the way out to the tips. But for the moment, let's go with the full span correction factor of 1.0. We take our delta of the flaps maximum coefficient lift multiplied by our flap span, 0.7, which would be 70%, divided by our full span, which would be 100%, and that gives us a change in wing coefficient lift of 1.05. So we can take our 1.275 that we calculated before, add 1.05, and that should give us our total wing maximum coefficient lift with the flaps deployed. That's what I'm showing right here. Now, like I said, we could do a linear interpolation to get a more accurate number. Since we're not at 50%, we're not at 100% for our flap span, we're at 70. So I'm saying, since Barnaby's conservative, and I don't feel like going and doing that linear interpolation, add 10%, which will be multiplied by 1.1 correction factor up here. And we go from 2.28 for the maximum coefficient lift of the wing to 2.4. I'd say that's pretty good. It should probably be a little closer to 2.5, 2.48, something like that. But 2.4 is fine. That should give us a little margin for error. Now that we know the maximum coefficient of lift for the wing, we can calculate the wing size. Previously, we had gone through the calculations of figuring out a potential wing size by using a coefficient of lift of 2.0. And that was using the FAA's method of calculating an ultralight's wing size and stall speed, etc. We came up with a wing surface area of 108.5 square feet. And we talked about how to do that also in the UWS-1Design Wing Size Part 1 video. Now using this and our new coefficient of lift, we can calculate a new wing size. And that's pretty easy. We take the old wing size, take the old maximum coefficient of lift of the wing, divide by the new maximum coefficient lift of the wing, and that'll give us our new surface area. So if we plug in our 108.5 square feet, our old coefficient lift at 2, our new coefficient lift at 2.4, and we come up with a grand total of our surface area for a wing of 90 square feet. In determining our wing dimensions, in this case the span and the chord, we have a couple of competing goals. One is that we'd like to keep our chord of our wing fairly long to get higher Reynolds numbers, because our airfoil will perform better at higher Reynolds numbers. But we'd like to keep the aspect ratio fairly high, and if you remember, aspect ratio is the length of the wing divided by the chord of the wing. We'd like to keep that high to keep our wing efficient. By having a higher wing efficiency, we have lower induced drag. But when we increase the aspect ratio, we almost always have to reduce the chord length if we have a fixed wing size. So these two guys are competing. Well, I could go through some lengthy analysis to try to come up with an optimum value for that chord length, but I'm just not going to bother. I'm going to play it by ear here. And if it turns out to be less than optimal in the future, I'll just design another wing. What I did is I created a wing area spreadsheet calculator. Since this wing is not tapered and not rectangular, calculating the area on it's a little bit tough, so I made a little spreadsheet calculator that would do it. After playing with it a little while, I decided an aspect ratio of roughly 7 keeps my root chord from getting too small, but still gives me a fairly large aspect ratio to try to keep my efficiency up. I would like to have the root chord a little bit higher, but I'm going to go ahead and work with a root chord of 3.9 feet. And that makes the tip chord 1.95. I kept that as a 2-to-1 ratio. And as I mentioned up earlier in the second slide, the wing span comes out to be 27 feet. Let me describe fairly quickly how I calculate the wing area. I use the Open VSP program to draw and configure the wing. And this green gizmo here is the wing, and I can set some parameters in the program to automatically section this wing. And the way I've sectioned it is here where I have almost no curve on the leading or trailing edge, I have fairly wide sections. But here where it curves more and more, I put the sections closer together. And by doing that, I can get a fairly accurate calculation of the wing area by calculating the area of each one of these rectangles. They're not really rectangles, they're more like trapezoids, but I can calculate the area of these trapezoids and add them all up and get the wing area. Now I wanted to do a spreadsheet to do this so I can actually play with span and chord in the spreadsheet and have it calculate the wing area for me. So what I did in OpenVSP is I probed each one of these leading edge points and got a X coordinate, which is fore and aft, and a Y coordinate, which is out along the span, with 0, 0 being right here at the root at the leading edge. And I also did the same thing on the trailing edge, and I put those coordinates into a spreadsheet and then normalized them. And here's the spreadsheet I did, and over here on the left-hand side are the normalized planform coordinates. So here in this column is the Y coordinates starting at 0 at the root and extending to 1 out here at the tip, and that means it's been normalized. Basically what I did is I took the actual coordinates from OpenVSP divided by the span, which gives us 1 at the tip and 0 at the root. Now in the X direction, which is fore and aft, I have a column for the leading edge and a column for the trailing edge. The leading edge at the root is 0, like I mentioned before. The X position of the trailing edge at the root is 1. Then when you get out to the tip, we start going through the curves. And as you can see with the Y's, they're fairly close together out here toward the tip, but toward the root, there's a little more distance between them. And if we come out here at the tip, the normalized leading edge position is at 0.3, normalized trailing edge position is at 0.8. If you remember, our taper ratio is 2 to 1. So if you subtract this 0.8 by 0.3, you get 1/2, which is half of 1. So we still have our 2 to 1 ratio. So to go from our normalized coordinates out to real coordinates, I've set up this calculator. So for the span, the Y calculation, we take a semi-span, which is 13.5 feet, and I can change this number to whatever I want to. And what it'll do is it'll go and calculate what I'm calling wing station, which is the real Y coordinate. So at 13.5 feet, we start at 0 at the root and come down to 13.5 out at the tip. And then I've done a similar thing for the leading edge and trailing edge. And here I can enter a value for the root, which is 3.9 feet. It'll calculate the leading edge X coordinate and trailing edge X coordinate. Now what I then do is calculate area for each one of these sections. So if you look at two of these rows together, this row is going to represent one side of a section. The next row will represent another side of the section. Basically, these are coordinates for a trapezoid, and I can calculate the area for the trapezoid and put it here. So I calculate the area for all these trapezoids down through here, and I sum them all up, and I get 90.2 feet. Now I can change the area by changing the span and the root chord, and it'll automatically go through and recalculate all of it and give me a new area. I also have it calculate a couple other numbers for me. Calculate the aspect ratio, and it'll calculate the thickness in inches. So if I change the percentage thickness, and this is percentage of the chord, this will then calculate what my maximum thickness of the wing will be. All right, let's talk about the MAC, or the mean aerodynamic chord of this wing, for just a moment. We talked about how to calculate the mean aerodynamic chord in an aero terminology video. And this is not a rectangular or trapezoidal shaped wing or tapered wing, so it is a little more complicated to calculate the MAC, just like it's a little more complicated to calculate the area. But just in case you only care about the results, the mean aerodynamic chord is 3.43 feet. Now the root chord was 3.9, so you can say it's a little bit less than that. The X position of the mean aerodynamic chord is 0.253 feet, so we're about 3 inches back from where the leading edge of the root chord is, and the distance from the root is 6.8 5 feet basically. So a little over 6 feet out from the root is where the mean aerodynamic chord is located along the span. I'm not going to make you suffer through the explanation of how I did all the mean aerodynamic chord calculations, but if you go back and look at that aero terminology video I just mentioned on the mean aerodynamic chord, I put the equations in here from that video. And so we have basically the Mach 0 through Mach about 54 spots that I calculated. Yeah. So Mach 0 through 54, so that's each section I calculated the Mach for. And then we also needed to have a sum term, and then we divide each calculated Mach divided by the sum term, and then you add all those up, and you get a 3.43. That's basically it. Then I did the same sort of thing for the Y value and the X value for the Machs. So down here, that roughly 6.15 for the Y position of the Mach, and that 0.25 for the X position of the Mach. That's about all there was to it. Alright, so we finally got through that. Now, what are we going to do next on the design of the UWS-1 Ultralight? Well, we need to figure out what our moment arm is that the horizontal tail has to handle. So that's going to be the wing pitching moment and the moment caused between the distance between the center of gravity and our aerodynamic center. Once we have that, we can start on that horizontal tail design, at least the aerodynamic part of it. And we're one step closer to start making some parts for this airplane. If you're new to the channel and you'd like to be notified when some more of these design videos come up, all you have to do is subscribe and then hit that little bell button and you'll get notified when a new design video comes up on the UWS-1 Ultralight Airplane.